So as I will continue with the Bohr's model of an atom, okay, and derive two formulas. So
derive.
do it a formula derive Gorm. So we'll continue with the Bohr's model, okay? Bohr's model continue Gorm, and we'll find two formulas. We'll try to derive two formulas. So in the last class I told you about Bohr's model, right? Bohr's model Bohr's model electron can move out by gaining energy and they'll fall back to their parent state by releasing energy, right? Releasing energy. Yeah. So this can be done. And Bohr's model of an atom is basically a modification of the Rutherford model of an atom, right? So some questions that Rutherford could not answer was answered well by Bohr's model of an atom, right? And some major improvements were also carried out. So this type of the released energy, right? This energy can be visible light, can be some other high energy radiations like gamma, X-rays, etc. Right? So this can be anything. This was like addition to the theory postulated by Rutherford. Now one more addition to the Bohr's model of an atom was this one. So we know that an electron revolves around the nucleus. Yeah, we know that every electron revolves around the nucleus in definite orbits, right? Definite orbits. They have a particular parent orbit. They know which one is their parent orbit, and they revolve in that orbit. Now, according to Bohr's theory, an electron revolving around a parent orbit will always have an angular momentum. So they'll have an angular momentum. So this is an important thing you need to know: angular momentum, which will be equal to the multiple of h by 2 pi. So h is the Planck's constant and 2 pi 2 pi ho. So angular momentum will depend on is the nth multiple of h by 2 pi. So n is the number of orbits. So if the electron is in the first orbit, n is 1. If the electron is in the second orbit, n is 2. Like that. If electron is in the third orbit, n is 3. So the angular momentum of electron revolving around the nucleus in some definite orbit is the n multiple of h by 2 pi, where h is the Planck's constant. Planck's constant, right? So it'll always be this value. So if an electron is revolving around the nucleus in the first orbit, then n will be 1. So the angular momentum will be h by 2 pi. So for instance, like if you know what momentum is denoted by p. Momentum is basically mass into velocity. So anything कोई चीज को mass multiplied by its velocity will give you the momentum. Now to find angular momentum, let's say this PANG, angular, you just need to multiply the angular component here. So angular component here is radius. So angular momentum is mv into r, or r into m into v. So you can write r cross m into v. So this is the way to write it. So you don't need to worry about this, how to write it. Just you know that. Just remember that angular momentum is the angular component, that is the radius, multiplied by m into v. So this is the basic basic momentum formula, m into v. Now when you multiply that with radius, you get angular momentum. So r into m dot v, r cross m into v equal to n into h by 2 pi. So let's consider this equation as 1. So the angular momentum of an electron revolving around the nucleus is the nth multiple of h by 2 pi. So nth multiple of h by 2 pi in the sense it is n बनेगा, the number of orbit, the orbit number in which the electron is revolving. So the angular momentum of an electron will depend on the orbit in which it is, right? Because h by 2 pi is always a constant. 2 pi is always a constant number. H is always a constant number. It's a Planck's constant, right? So the only thing that the angular momentum will depend on will be the value n, right? It will not depend on any other thing because it's n into h by mv. H is constant, 2 pi is constant. So let's remember this point for now. R into r cross m dot v equal to n into h by 2 pi. So this is basically vector multiplication. So this cross product one, like dot product one. So this is called dot product. So this is the vector component, this is the scalar component. You don't need to worry about this right now. So let's take this as equation 1. So r into r cross m into v, m dot v equal to n times h by 2 pi. Then what do we do next? So I think yesterday we came to a conclusion. We derived this thing, right? So centrifugal force mv square upon r is equal to the centripetal force. So centripetal force in this case was 1 by 4 pi epsilon naught e square by r square, right?
Square.
So e square by r square. So we were just considering that the centrifugal force of electron revolving. So if this is the nucleus and electrons are revolving, so the centrifugal force is mv squared upon r. So this is the centrifugal force, and this is exactly balanced by the pull by the protons. So it is completely balanced by the pull by the protons. So this is the pull by the proton, 1 by 4 pi epsilon naught e square upon r square. So we mark this equation as 2. So the first equation was the one where we found the angular momentum, and second one is this equation. Now what we do is let us generalize for nth orbital, let's say. So we want all of these formulas to be in terms of nth orbit. So everything in this equation will remain the same except two quantities if when the n changes. So if electron is moving up or down, everything will remain same except two. So these two things are radius and velocity, right? Others, everything will remain the same. Mass is always same, 4 is always same, pi is always same, epsilon naught is always same, and E is always same. So what we get of a generalized formula is mvn square divided by Rn equal to negative of 1 by 4 pi epsilon naught into E square divided by Rn square, right? And the other formula that we had, like Augie derived गरेको, Rn cross m into V equal to this was n into h by 2 pi. So now here this will also be Vn. So only velocity and radius will change if the electron is moving up and down, right? Nothing else will change. Mass of the electron will remain the same and everything else will remain the same. Now what we do is, let's divide these two equations. This is equation 3 now, and this is equation 4. Now let us divide these two equations. So when we divide these two equations, we get mvn square divided by Rn equal to negative of 1 by 4 pi epsilon naught into E square divided by Rn square whole divided by Rn into m into Vn equal to n into h by 2 pi. So we get this when we divide, right? So now we cancel it off and we get the value something like this. So we get Vn equal to 1 by n into E square by 2 pi 2 epsilon naught into h. So this is the final what we get after dividing the terms. Okay, you can try it, you can divide it, cancel it and check you will get this or not. So now for the time being we are omitting the negative sign here. We don't want to keep the negative sign. You know, this negative sign doesn't like put any value to the thing. So it does give it just give you idea about the direction of the force, right? So it just tells you that the force is repulsive, force is attractive because it's between an electron and the proton, right? So it is attractive. So to signify that, we just have a negative sign, but for the time being, we are just omitting this negative sign. Let's forget about this negative sign. Okay, so we get the value of Vn as 1 by n E square by 2 epsilon naught h. So now if we put the value of n as 1, so velocity of electron in the first orbit is E square divided by 2 epsilon naught into h. So this is the value of velocity of electron in the first orbit. It's very, very important, not in your only 12, like 12 ko basis ma matra important haina. This is important for every, like if you go on like physics further liera gayo ya ta engineering further liera gayo ni, this is one of the important topics you'll get. So this is the velocity of an electron in the first orbit, right? So similarly you can put the value of n like anything else. You can put the value of n and check the velocity at every orbit, right? So this is how you do it. Okay, so is this clear? It's clear, right? Okay, so now what we do is, we had an equation. Where was that equation? Okay. mvn into Rn. So we had one equation somewhere here. Where is that? Yeah, here. So Rn into m into Vn. So we just found Vn, right? We just found the velocity Vn. So what we do is we put the velocity Vn in this formula. So what do we do here is, so Vn is 1 by n. So the formula was m into Rn
Alright.
m Rn Vn equal to n into h by 2 pi. So what we do is we just put the value of Vn here. Rn into Vn is 1 by n e square by n e square by 2 epsilon naught into h equal to n times h by 2 pi, right? So this is the thing that we get. Now what we do is we substitute the value and take everything to the other side and keep it for Rn. So Rn will be equal to n h by 2 pi multiplied by 1 by n e square by 2 epsilon naught. No, wait. So यो सबै डिवाइड हुन्छ. So n by h by 2 pi divided by m into 1 by n e square by 2 epsilon naught into h. So this is the value of Rn.
Substitute for.
So this is m mass. So mass, yeah. So where is n? So यहाँ एउटा n छ, right? So this n and this n will go up and multiply. So you get the formula as n square epsilon naught into h square divided by pi m e square. So how do you get this? So this n will go up and multiply with this n square boy, right? So this h will go to the numerator and multiply with this h, we get h square. This epsilon naught will go to the numerator and multiply with h square, so epsilon naught. All right, this 2 and 2 will cancel off, so this 2 and this 2 will cancel off. Then this m stays in the denominator, m. There is another pi which comes down to the denominator here, and e square will stay in the denominator. So this is the formula for the radius, the Rn value. So radius of the electron in the nth orbit is given by n squared epsilon naught h squared divided by pi m e squared. So this is a very important formula. So now when you substitute n as 1, so when you substitute n equal to 1, you get r1 equal to, so radius of the first electron orbit is given by r1 equal to epsilon naught into h square divided by pi m e square. So this is for every case. For every atom you can find the value of the radius of the first electron orbit or second electron orbit. You just put the value of n. So n second over n ko badli you just put 2, so 2 square will be 4. So this thing will be multiplied by 4. Okay, is this clear? Okay, copy. Right? Clear? This part is clear, right?
Oh, sure.
Yeah, that's clear. So okay. So now what do we do? So this is very important. This is in the syllabus as well. So syllabus man saw, and it is very important as well. So with this formula you can find the radius of the electron orbits, and with this Vn formula, where is that Vn? So with this Vn formula you can find the velocity of nth orbit. So nth orbit. Okay. So now this is for the Bohr's model of an atom. So there is one more derivation. I think it's about energy. I don't know if it's there in the syllabus or not. I'll check it. But even if it's not there, I'll try to solve it for you. It's very simple, very interesting as well. I don't think it's there. Okay, let me solve it. Okay, but still. So for Bohr's model of an atom, so energy is given by negative of 1 by 2 e square divided by 4 pi epsilon naught. So basically we write it something like energy equal to negative of e square divided by 8 pi epsilon naught. I think here we have r. Here 8 pi epsilon naught Rn. So this is the energy in Bohr's theory. Okay, Bohr's model of an atom, energy is this formula. Okay, now what we do is we substitute the value of Rn. So what was Rn that we got? So Rn was n square n square epsilon naught h square pi m e square. Epsilon naught h square pi m e square. So this was Rn, right? So now what we do is, in place of Rn in this formula, we replace Rn with this one, right? We replace Rn with this one, so we get E equal to minus E squared 8 pi epsilon naught Rn square. So this is n square epsilon naught into h square divided by pi me squared whole square, I think. N squared pi me squared whole square. Where is the whole square? So why is the whole square there? So this is the energy of Bohr's orbit. Energy equal to negative of E square 8 pi epsilon naught Rn, right? So now previously we just found the value of Rn. So we just derived the formula of Rn. Rn was n squared epsilon naught h square pi me square, right? So now we are putting this value in this equation somewhere here. So we are just doing this like this. So now we come to a final formula of energy. That energy now will be En. En will be negative of 1 by n square m e to the power 4 m e to the power 4 divided by 8 epsilon naught square h square. 8 epsilon naught square h square. So this is not there in the syllabus, but still it's very interesting. So energy of an nth orbit. So when we all like cross multiply, take it to the numerator, pi will cancel off, right? Pi will cancel, epsilon naught will multiply and form epsilon naught square. This h square will stay in the denominator itself. 8 will also stay in the denominator. N square will also stay in the denominator, right? So me square will go to the numerator. So m will go up, m into e square into e square is e to the power 4. So this is the formula of En, right? Now what we do is let us take n is equal to 1. So when we take n is equal to 1, we reduce the formula as m e to the power 4 8 epsilon naught square into h square, right? So now when we put the values of m e to the power 4 8 epsilon naught square h square, we get a value of En. So that is minus, this is a constant value, you should remember it, minus 13.58 eV. So this is the energy of the first orbit, not En, this is E1, okay? Because in place of n, we are replacing n with 1. So E1 equal to this. So E1 will be equal to a fixed value of minus 13.58 electron volt. Is it correct? Yes, minus 13.58 electron volt. So we get a generalized value of E for the first orbit. So this is for the first orbit, right? First orbit. Now for any other orbit, n is given by En, or energy of n is given by minus 13.58 divided by n square eV. Is it clear? Because now what I did in this place was, so what I did was I just replaced n with 1, right? So when I replaced n with 1, so this thing becomes 1, right? So we don't consider this now. So I put the value of mass, E is the charge of an electron, epsilon naught is permittivity of free space, and h is the Planck's constant. So your work for today is you find all the values. So m ka value got you, just try to find what is the value of m, find what is the value of E, find what is the value of epsilon naught, find what is the value of h. Okay, so h is the Planck's constant, epsilon naught is permittivity of free space, m is mass, and E is the charge on electron. So what I did was I substituted all the values here. So I substituted the values of m, E, epsilon naught, h, then I found that E1 equal to this whole thing. When I solved it, I got it as minus 13.58 eV, right? Electron volt. So this is the energy on the first orbit, right? Now if I change the orbit, if I change n, if I change from 1 to 2 to 3 to 4, etc., nothing will change, right? E is a constant, m is a constant, epsilon naught is a constant, h is a constant. So only thing that's changing is n square. So the energy of nth orbit can be generalized as minus 13.58 divided by n squared eV. Is it clear, this part? This is not there in the syllabus. Copy कर दो.
Interesting.
Okay, copy. So with this formula, you can find anything. Okay, you can find the energy of any orbit in a atomic system. So you have an atomic system with nucleus in the center and electrons revolving, right? So with this formula, you can find the energy of any revolving electron, wherever the orbit is. In the first orbit, 20th orbit, 40th orbit, whatever orbit it is. Okay? Jati when you can use this. Because nothing is changing at all, like except for n. But this is like not a like completely accurate measurement. Okay, so there might be some abnormalities with the mass. So mass might change because like when velocity increases, there is a relativistic increase in mass as well, right? So when velocity increases, mass will also increase, right? So we have not considered that part here because we don't expect that to happen in the atomic level. So we don't expect the electrons to move so fast that their mass will increase, right? So that is a type of abnormality that we do not consider. That may be possible, may not be possible. I don't know it. It's not required in your standard as well. But always that the why question, the why question should always arise, right? Why? Why is this abnormality? Why is this not happening and why is this not? So if that question arises, just think about we are considering the idealistic system. So we are considering a system which is ideal at all cases, right? It's totally ideal. So it doesn't become a practical system. It may be a practical system as well. I don't know, right? But for this case, we are considering an ideal system where the relativistic mass, that is the mass that changes with respect to velocity, is not considered at all. Okay, we don't consider the change in mass or change in increase or decrease in mass with velocity. Okay, so this is the energy thing. Have you copied this? Done?
Got it.
Okay, so we have our last one diagram. I'll just do one diagram and that's the end of the class. So मैले अस्ति भने I told you about this thing, right? I can't draw a straight line. Wait. So this is the first orbit. This is the second orbit. This is the third orbit. Spacing increases. This is the fourth orbit. Now you know why this spacing is increasing abruptly? Now this is actually the energy level diagram. Okay, these lines represent the energy of orbits. Okay, energy of orbits. So this is the first orbit. This is the first orbit. This is the second orbit. This is the third. This is the fourth. This is the fifth, and this is the sixth. Right. So हामीलाई थाहा छ कि formula of energy we have some constant that is minus 13.54 divided by n square. Right. Wait, la. So we know that there is. Sorry, I did something wrong, I guess. So this is the energy level, energy orbit diagram. So this is the energy state diagram. So we know energy is like inversely proportional to n square, right? So more this value increases, more energy will decrease. Okay. So if denominator is increasing, so if I have more in the denominator than the numerator, then this value will decrease as a whole, right? So the maximum energy will be in the initial state. This is called the ground state. Right? Because where here n is equal to 1. So when n is equal to 1, energy is minus 13.54 eV. So let's say this is minus 13.54 eV perfectly, right? Now when the n becomes 2, this will decrease, right? So the value is less than 13.54. So let's say there is an energy 1, E1, then E2 when n is equal to 3, then n equal to 4, n equal to 5, n equal to 6. So we are spacing it, yes, spacing got out there because we want to fit more values into it. Okay, so E3, E4, E5. So now this is the ground state of an atom. So ground state of an atom, of an electron. So when an electron is in this orbital, this is the ground state. So as the electron gains energy, it goes to like some higher states. So these are the excited states or excited energy levels, right? So now when the electron falls back again, it'll lose some energy, right? The radiation energy, and this energy can be viewed in some cases. So we can see the energy sometimes. It's visible light, or it may be infrared, or all those things. So this is how you draw an energy level diagram. So this is the ground state when n is equal to 1. Then when n keeps on increasing, that will be the excited state or excited energy levels of an electron. So it can go up, rise up after gaining some energy, but it will ultimately fall down to its ground state, right? Because the ground state is the most stable state of an atom. So everything goes for stability, right? So everything wants stability. So for for an electron in this state, n equal to 3. So if an electron is here, this will be the ground state for that, right? This will be the ground state or the neutral state, right? Now when it gains energy, it will go up, and when it loses energy, it will fall down again to its ground state, right? It is not a hard and fast rule that this is only the ground state, okay? With respect to this electron, this is the ground state. Clear? So with respect to this electron, this is the ground state again. This line, this energy line is the ground state, right? So it will depend on the electron you are considering. So is that clear? Okay. So
N2
N2. Okay, so if electron is in this state, so this is the ground state for this ground state. If the electron is in this energy level, this is the ground state of the electron. It may go up somewhere. Let's say it goes up to here, right? It'll ultimately fall back here and it'll give out energy. So the farther it climbs,
we can consider anything as ground state.
exactly, it depends upon the electron, but you can't just consider like if I have an electron here, you can't say that E3 is the ground state. Okay, so if this is the electron, the energy level in which it is, it's the ground state. Okay, so now if you consider this electron which is in the second n equal to 2, then this is the ground state. Okay, it depends on the electron you're considering. Okay, you can't just blindly take anything as the ground state. And one more thing, one more important factor that you need to know. Wait. So let me see. How can I explain you that? So let me assume some two movements of electrons. Okay. So one movement is when this electron climbs to this state, right, and it comes back, and it's releasing some energy. So this, let's say this is energy 1. E1R, so energy 1 released. Okay, so there is another electron in this state, right, and that electron is climbing till n equal to 6, right, and it's falling back from n equal to 6 to n equal to 1, right? So I have another electron in the same state. It's going up there and it's coming down here, so it will release some energy, right, when it comes down. So E2R. Now which one will be greater? E2R will be greater or E1R will be greater?
E2, no?
E2R will be greater every time. It is excited to a higher energy level. So let's assign a value. Okay, let's assign the ground state to be 0 electron volt. Okay, so ground state is 0 electron volt, and let us assume that the energy increases to 2 electron volt here, to 6 electron volt here, to 8 electron volt here, to 14 electron volt and 16 electron volt, right? So now this electron goes to 6 electron volt and comes back to 0. So the total energy that is released is 6 minus 0 equal to 6 electron volt, right? Now this electron, same electron from the same energy level goes to 16 electron volt and comes back. So the amount of energy released is 16 minus 0 equal to 16 electron volt. So this is E2R, right? So energy of the second electron that is released, then this is the first E1R. So at any case, E2R will always be greater than E1R. Okay, so if electron is like getting excited from the same state, right, and it reaches a higher level than the other electrons, then it will release more energy compared to the other electrons when it falls back to its same state. Okay, clear? Ekdam clear, right, this part? Nice. So this is the end of this topic from Bohr's model of an atom. So we did Rutherford's atomic model. Then we did Bohr's atomic model. So we did two major atomic models that actually shaped the atomic model theory. So first one was the Rutherford. So we did the alpha particle scattering experiment, right? Then we did the Bohr's atomic model. So Rutherford's nuclear atomic model. So nucleus was first discovered there. Bohr's model of an atom, we found energy, right? We found the formula for energy. We found the formula for velocity. We found the formula for radius, right? And this formula can be applicable till now. This can be used like earlier someone we can use it, right? And we learned about how electrons get excited, how they fall back to its parent state and release energy, right? So we did this. So the last topic from this chapter that is left is hydrogen spectrum. Which I'll not do today because this much is enough for today. So I'll start a hydrogen spectrum tomorrow and I'll complete it by day after tomorrow. So 2 more days I'll complete this chapter. Okay,
Yes, after
so
this,
if you have yes, your chapter is okay. After this we'll do one more chapter from this unit. So there is one more chapter called Photoelectric Effect. That is also very interesting. So how photons can influence the flow of current. So how can light cause electricity to flow? So that is the chapter we'll do after this, and we'll end this unit from by doing this chapter, and we'll complete X-ray and other part later. Okay.
Okay.
So if you have any questions regarding this right now, you can ask me right now, or if you have any questions while revising it, just let me know.